introducing Alexia for those of you that don't know her. So she is French. She did her PhD with Serge Haroche on the Schrödinger cat states of light, doing experiments, I might add. And then she switched to doing theory, and she moved, became a scientist at the CNRS, where she was a senior scientist at the Institut Néo in Grenoble, in France, for a number of years. And then recently she moved to become the director of the Maju Lab in Singapore. So made a big jump to another side of the world, and she directs the CNRS lab. That's the very fancy French society for excellent physicists there. Also, they have a colony now in Singapore that Alexia is the head of. And recently she was awarded the Chevalier de l'Ordre National du Mérite. So it's just like the French knighthood. So very nice honor for Alexia. And of course, we've been working together with Alexia for a number of years now. She's an expert on quantum thermodynamics, among many other things. We're very pleased to have her give our public lecture for the Institute for Quantum Studies. So let's welcome Alexia.
Thank you very much for the introduction, also for your patience, the audience that is remote. I gave the talk this morning and I was already happy to be here. I must say I'm still very happy to be here. I learned lots of very nice things throughout all the day. And so I'm not leaving now, in other words. So the title of the workshop is Quantum Energetics. The title of my morning's talk was Bipartite Quantum Energetics, and now it's Quantum Energetics, Fundamental and Application. So I think I'm still in the scope. And I'm going to start by introducing very shortly, where we come from in quantum energetics, which actually requires to go back to good old grandpa thermodynamics. So we shall start by that, because you told me it was a public talk, so I anticipated that not all the audience would be physicists. So I'm going to take a very high-level point of view on all that. And the game of the first part is really to bring us from locomotive down to measurement powered engines and quantum energetics. And that will be actually the second part of the talk, which is understanding what is quantum energetics, but at the very fundamental scale, like when we look at quantum devices. And so then, we'll mostly talk about the measurement powered engines that we have worked on together with Andrew and Keter for a while now. And the last part of the talk will be devoted to another possible aspect of the work, which is, let's try to zoom off a bit. We have small quantum devices where quantum energetics is good, but then we can also try to see what is the impact of this fundamental research at the macroscopic level, and typically in the very fancy field of quantum technologies. And can we relate, I would say, the two levels of description, and what does it bring out? So that's the program. So I promised grandpa thermodynamics, so here it is. In grandpa thermodynamics, you do have systems that are like working substances, and these working substances, they can exchange work with batteries or operators on the one hand, and on the other hand, they can exchange like heat with thermal bath. And with this very simple and paradigmatic scenery, you have the first law, which is the playground for engines, and that tells you mostly about energy. And then you have the second law, which basically tells you about thermodynamic time arrow, irreversibility, and this is basically the realm of no-goes. You shouldn't do this. You don't have the right to do that. And actually, if we put together the first law and the second law, what we extract are fundamental bounds. So heat cannot propagate from cold to hot. You cannot run an engine just with a single thermal bath in a cyclic way. All these kind of things that actually basically come from the reunion between first and second law. And this also gives us access to optimal efficiencies. So you see that actually we have like a very virtuous circle between what is very fundamental, which is time arrow, and what is very practical, which are engines. That's, I would say, the miracle of classical thermodynamics. It's like engineers and fundamental researchers, they really work hand in hand. Okay, so that's for the 19th century. And actually, at this time, there was, okay, I want to comment on Kelvin-Planck no-go. I promised you no-goes before. So the most famous no-go theorem is probably the Kelvin-Planck, which tells you that basically we cannot extract work continuously from a single hot bath. And the best way to understand this law is to focus on the Carnot engine. In Carnot engine, you typically have like two major steps. One step where you have a hot gas that expands, which corresponds to the work extraction step. And actually at this point of the engine, you need to reset it. So bring it back to its initial position so that you can restart the engine. And this need for resetting the gas, actually this explains why you need not only a hot bath, but also a cold one. Because if you were using the same bath, then you would pay as much work to compress than the work that you extracted. So this gives you an idea of why we need these two temperatures to please Kelvin and Planck. And so why am I saying this? Why am I recording these things? Is that starting from this point comes the idea of information. Actually, this is the idea of Maxwell-Demon, which his sense is to say, okay, for this reset step, do we really need to pay work? Because if I have access to all the microscopic degrees of freedom by measuring where are the particles of my gas, then I can just pick them up, put them back in their initial position, and the job is done. And I haven't paid any work whatsoever. So it looks like with this Maxwell-Demon, I can extract work from a single hot source. And so where is the trick? How did we violate the second law? Well, basically, the resolution of the paradox, it took like more than 1 century to solve this. And it's the famous information is physical of Landauer, Bennett, Szilard, etc., which tells us that what we have to do is to erase the demon's memory to close the cycle and then get back to our second law. So this is the entry point of information thermodynamics. And in information thermodynamics, actually, the favorite system is a bit of information. And for this, actually, we can reuse the picture of the Carnot engine to understand what's going on. Now, let us imagine that instead of having a mole of particle, we just have one. And this particle, this very special gas, can be on the right or on the left of the vacuum chamber. This is a bit of information. Say left codes 0 and right encodes 1. And so let us try to reinterpret the Carnot engine with this ideal gas. Well, the expansion step, where we start from a known position of the particle and we let it expand, it corresponds to what is known as the Szilard engine. And at the end of the expansion, what we have is that we have lost one bit of information because we don't know anymore where the particle is. And at the same time, we have extracted one elementary bit of work, which is the increase of entropy multiplied by KT. KT is, always the magic translation between energy and entropy, as I was saying this morning. Okay, so that's for the Szilard engine. And the other step, it's even more well known because you start from a state of the bit that you don't know, and then you pay some work and you reset it in the 0 state. And with this, you have access to Landauer's erasure work. Okay, and this information thermodynamics experiments, sorry, oops, I said the word. This Gedanken experiment became a reality. Well, it's starting to be like more than 10 years ago now. There was a magic year, 2011, where both Landauer's erasure and the first Szilard engine were implemented respectively in my hometown in Lyon and in Tokyo. And so the idea is that this is actually, again, the entry point to another field, because what you are probably aware of right now is that we have left the field of macroscopic thermodynamics, where we have huge amounts of particles to play with. Now we actually play with very, very small systems. So that's the scenery of thermodynamics, but now instead of having a large amount of particles, we just have a little guy here that still exchanges work with some guy that controls it. And at the same time, exchanges heat with a bath, but now the bath induces very, very large fluctuations. And basically, these fluctuations, they cannot be neglected anymore. So at this point, you have entered what is known as stochastic thermodynamics. And stochastic thermodynamics is really the part of thermodynamics where systems become very small and fluctuations become predominant. And in this kind of new scenery, we can revisit these ideas of work and heat. What is it at this level? Well, work, what you try to do is when you build a nano engine, you try to extract work from these thermal fluctuations. And so basically, an engine at this level of description, it's a rectifier for fluctuations. On the other hand, these thermal fluctuations, they are the mere reason why there is irreversibility, because they signal a lack of control. And basically the fact that your system on which you're trying to implement some protocol, you won't be able to rewind it at will. So basically, irreversibility in that picture, it's deeply rooted in the idea of randomness. So the take-home message here is that stochastic thermodynamics is really based on randomness, and this is something that will play a strong role later on. So please keep that in mind. So now, actually, at this point, we can start to think about how the game of quantum thermodynamics started. The game of quantum thermodynamics, we can say it started that way. We pick the scenery that is on this slide here, and instead of playing with classical quantities, we pretend that all these guys, they are dived into a Hilbert space. So here, actually, the game is that we are going to, what I wanted to say here is that if we pick a bit and we claim it's actually pertained to a Hilbert space, now there is a possibility that it becomes a qubit. So there is a possibility that we can drive this beast coherently. And the idea of quantum thermodynamics in that field, and to see, I'm trying to go faster. And just a question, how many of you are not physicists? Okay, so because I was, there are some faces I know and say, oh, the poor guys, they're really going to get bored, but no, okay. So I still talk for someone, and I really thank you to be here. So yes, so I come back to my point. Quantum thermodynamics, it's basically picking up, you can phrase it that way, the scenery of stochastic thermodynamics, where there are small systems that interact with big baths and big operators, and start to take into account the fact that they can be quantum. And typically before we played with a bit, and now we are going to play with a bit that can be quantum, which is a quantum bit. And if you follow a little bit the news, you know that the quantum bit or the qubit is actually the building block of emerging technologies, which are called quantum technologies, which hold the promise to communicate faster, compute faster, communicate in a safer way, and induce like more precise measurements that in the classical world. And the qubit most general state, there are superposition states. And these superposition states, they are at the origin of the quantum advantages that we are like sold that will change the world. There is a reasonable amount of quantum physicists that work in that business now. So that's the idea. And so actually this idea of quantum advantage, so as far as I know, it started to emerge in the business of quantum technologies. But in quantum thermodynamics, we started to search for quantum advantages in the same way. So in the same way, quantum coherence and entanglement, they can be used to compute faster, blah, blah, blah. Maybe if we try to extend the rules of thermodynamics, taking into account quantum features, we can hope to have quantum engine that outperform classical engine. We can build quantum Maxwell daemon that, again, perform better. And then at this level, you can start to investigate what is quantum irreversibility, what are quantum fundamental bounds. So basically all the concepts that we have seen in classical thermo, how can we reinterpret them if there are coherences and entanglements? And so actually, and now I'm slowly coming to the impact of quantum measurement in that business. So actually, one thing we have put forward when we have started to work in this is quantum measurement, and the fact that in the quantum realm there are not only thermal fluctuations, there are actually other ways to induce fluctuations on your system, and the most basic way is to measure it. So, for instance, if you imagine that you have your bit or your quantum bit whose state is psi theta here in the block here, and you measure sigma z. So basically, you ask to the qubits, are you 0 or are you 1? Then you are going either to measure 0 or 1, and at the end of the day, you won't be in the initial state anymore, which was psi of theta. So you do something that is very strong on your qubit. This is called the quantum jump, or this is the signature of the measurement back action. And so the bottom line is that since quantum measurement perturbs the system state, there are quantum fluctuations, measurement really appears as the ultimate dice here. And there is even more, actually, which is what you can do if you start from the ground state from the qubit, and you measure it along x, meaning you start from 0 and you ask your qubit, are you minus or are you plus? And here, so not only you have a quantum jump, but also you can acknowledge the fact that you start from a state which has no energy and you end up with states that have internal energy. So measurement itself provides energy to your system. It provides energy and it provides entropy, because at the beginning you are in the pure state, and at the end you don't know if you are in the plus or in the minus state. So you basically have the same sort of behavior between quantum measurement and a hot bath. And this actually brought us to the idea of trying to extract energy from these fluctuations that are absolutely specific to the quantum regime. So the strategy is the following. We start from the good old engine of grandpa, where we convert heat, which are thermal fluctuations at a small scale, into work. But instead of having a thermal dice here, what we do is we pick a quantum dice. And basically, here, we don't have a thermal bath anymore. We do have a measuring device, classical measuring device. And the game that we played is, can we extract work from this quantum heat with quote? You interpret it as you want. So in this, digging into the idea, we came with a proposal for an experiment where that is based on a quantum bit like this, that is coupled to some resonant light. So photons that have the same energy as the transition between the 0 and the 1. And if we do that, what we observe is what is called the radio oscillation, which is a coherent and reversible exchange of energy between the driving light and the qubit, which you see here. And this is an entropy preserving exchange of energy. So the qubit remains in a pure state all along the interaction with the field. So this is a work exchange, because changes of energy which does not affect the entropy of a system, this we interpret it as a work exchange. And now, what is the trick? So there are actually in this radio oscillation two possibilities. Either the qubit is providing energy to the field, which corresponds to the emission part of the radio oscillation, or the qubit is extracting energy from the field, which is the absorption here. So here, the emission is a good regime for the engine. That's precisely what we want to have. And this one is the one we want to avoid. So how can we do that? Well, the mechanism is kind of very simple. What we do is we stabilize the qubit in this plus state. And we do that and we feedback on it to keep it in the plus state where it keeps providing photons to the field. So you can see it as a new quantum Maxwell-Demon experiment where we basically don't need any hot bath to do the job, because this is the quantum heat itself that is converted into work. And the experiment, as far as I know, is done in Benjamin's group. So we just need to put ourselves at work and writing the results. And so this is the first idea of measurement powered engine. And then there is another one, which Andrew told about this morning, so which is based on the 2 qubits experiment that I'm going to briefly mention here. So imagine that instead of having just 1 qubit, you now have 2 qubits. And these 2 qubits, they have different frequencies. So you have a red qubit and a blue qubit. And you start putting some energy in the red qubit. That's the t equals 0 of the machine. And now you let the qubits interact. So the excitation that was in the red qubit starts to be delocalized between the red and the blue. In other words, you have created an entangled state between the 2 qubits. And now you perform a local measurement. In other words, you ask to the excitation, are you in the red qubit or in the blue qubit? And the fact is that there are 2 possibilities with different probabilities. Either the excitation is still in the red qubit, and then from the energy point of view, nothing happened, or the excitation is now localized in the blue qubit, and then it means that we have extracted energy. And if you take the average of the 2, on average, we have some energy gain. And this corresponds to an input of quantum heat. And the input of quantum heat, yeah, I was about to talk about non-commutation, but it doesn't matter. So, and this gave the idea of a Maxwell Demon engine with the very nice devil that was drawn by Leah, who is an artist and also a writer in the weekend. So that's it. It's good to have artists in the group. So, and that was a very nice job that we did together in COVID time. Actually, I guess that was the first paper of the project together. And yeah, that was a nice way to start. And now, actually, this brings me to try to define in a bit more like rigorous way what we mean by quantum energetics. So quantum energetics, it's everything that happens if you pick thermodynamics and you get rid of temperature. So it's the study of energy, entropy, information flows, and their relation inside the quantum world. And it's a cousin of quantum thermodynamics, but again, it's not necessary to have baths that are at equilibrium. The motivations, so sorry for, I said it this morning to the people that were already in the workshop, but anyway. So the motivation of this emerging field is that we can try to use quantum noise as a resource, not only the thermal one, but any kind of quantum noise. And this lies at the basis of measurement-powered engine, measurement-based cooling, quantum batteries, and the search for energetic quantum advantages or not that would come from coherence and entanglement. There is another kind of motivation that is more rooted into the second law, which is the search for the deep minimum of irreversibility in the quantum regime, and what is ultimately the cause of irreversibility at the quantum scale. And well, the more like technical business that comes with this are quantum fluctuation theorems and the establishment of minimal work cost, bounds, efficiencies. And also the question of the energetic advantage, are quantum resources good for energy efficient quantum technologies? So this actually brings me to the final part of the talk, which is this quantum energy initiative, where I told you that the idea is to pick quantum energetics with this very fundamental motivation I've shown you before, and to use the material that is produced in this fundamental area and to see how it impacts the macroscopic scale. And typically, the idea is to understand the energetic cost of quantum technologies, taking into account the full stack. So not only the little quantum processor that you take for granted. Most of the time in quantum thermodynamics, we really start from the quantum open system, but take into account the cost of building the classical context around here. So that's basically the goal. So that's the third part. And before entering into the meat of the subject, I will do a little bit more of philosophy by giving you, because actually the key concept behind all this is the concept of efficiency. So here I'm going to try to pick a very high level view of what an efficiency means. This is a machine. A machine is something that you build so that it does the job instead of you. And a machine, you need to provide it with food, so which are the resources. which can be energy or material. This defines the resource that you use. And then this machine, it implements a task and it reaches some result with some given metric of performance. And that allows you to assess the quality of the performance implemented by your machine. So the bigger the metric of performance, the better your machine proceeds. And the purpose of science and technology in general, when some machines come into play, this is to increase efficiency, not decreases them. And so in the realm of classical computing, this is a game that, the concept of efficiency is something that is very well known. So the machine is the computer, and this computer, you assess its how good it is if it can compute a lot per second. So the metric of performance here, it's the number of floating point operation per second, the flops. And the resource that you usually consider is the power consumption. And if you define an efficiency the way I did, well, you have performance per watt, which are flops per watt, which has the dimension of the inverse of an energy. And it's typically the energy that you need to activate one gate of the stuff, okay? So this actually efficiency, it's nicely increased over years. And here I just display since 2008, but actually if you look at the history of classical computing, it kept increasing. It kept increasing, eta doubled every 18 months. And it's known as Kumi's law, and it can be seen as, for the efficiency, the equivalent of Moore's law. Yeah, it's some sort of effective behavior, phenomenological behavior that we acknowledge, and we are happy with this. Well, now we are less happy because it's been more than 10 years, it has not increased, it saturates actually, which is a real problem in the CMOS technologies. And so this actually efficiency, it also allows you to benchmark the supercomputers, and you can build a ranking within the supercomputers, which is known as the Q green. No, not the Q green. The Q green is what we want to do. The green 500, okay, and which are the most efficient, energy efficient supercomputers with a state of the art that is 52 gigaflops per watt of last year. So this brought you the context. So now it is well known that actually we are living in an era where we use more and more computers, we consume more and more data, and we nowadays consume more than 11% of the global electricity in information and communication technologies. And there is no expected gain in efficiency. There is also the raw material consumption that poses a serious problem with respect to building new machines. And so there is this need for a paradigm shift that you hear, and the hope that basically quantum technologies could bring something good in this area. So actually, what does it mean? What are the promises of quantum technologies and quantum computing, especially? Again, very high-level description here. This is the promise of quantum computing. You have a problem which is defined by its size, and here you have the computing time. If you use a classical computer, you have an exponential growth in the computing time, and the promise of quantum computing is to bring the computing time in some more reasonable time. To gain, actually. So here the performance, it can be defined as computing power, like problem size divided by time, if I want to apply this definition of efficiency I was using before. And with this very simple scheme, you can define a quantum computational supremacy and quantum computational advantage, where basically the quantum computer is shown to compute faster than the classical one. Okay, so these plots, they are well known if you use noiseless quantum computing. Now the problem is that quantum computers, they are noisy, and as soon as you start putting noise, you need to correct the noise. So you add error correction in the business, which represents more steps in your calculation, which increases the computing time. And also the fact that if you use classical computer, you can be smart and optimize algorithm. So this actually defines the business of most people that work in quantum computing these days. It is exploring the noise resilience of quantum supremacy and quantum advantage as soon as to start using real hardware, noisy hardware. And what are the new regimes that come with it? And with this, you can define different regimes. The fault-tolerant quantum computing that is large scale, the only fault-tolerant but small scale, the noisy intermediate scale quantum computing. So all this with people trying to define when a quantum computer will behave better. And so actually all this is looking at the computing time. And the question that we ask is, can we transpose a little bit the debate, and instead of focusing on the computing time, can we focus on the energy efficiency? And in there, what we would consider here would be the energy consumption of the computer with respect to the problem size. And then we can really transpose the concepts. Here we have a region where actually the quantum computer, taking into account the error correction, would consume less than the classical one. And here we have quantum energy advantages. Sorry, I'm losing a little bit the wire, but you see what I mean. I mean, can we define in the same way we have quantum computational advantages, can we have quantum computation, quantum energy advantages? So that's what we want to explore and here are the definitions. I'm not going to read them, but you see what I have in mind. And so actually, where is the problem here? We can play the game. I like launching polls in the audience. Do you think that with a quantum computer will consume more or less, if it exists one day, will a quantum computer consume more or less than a classical one? More. Okay, so you are in that team, the more team. Are there people of the less team, or you are all? Oh, okay.
I feel like it depends on the problem.
Sorry?
I feel like it depends on the computational problem you're trying to do.
Sorry, with the mask, I don't hear.
I said I feel like it depends on the computational problem.
Yeah, absolutely. So, yes.
I would say the same, because we'll always consume all the energy we have, and that's basically also when the idea of Javan's law that you mentioned, isn't it?
Mm-hmm. So yeah, en France we say fil mouche. You saw that Javan stuff that
Yeah.
I did not comment because also I'm always very upset by this paradox, because to me it's really an artifact. It's economic paradox. So, but here I want to focus on physics, and because then if we increase efficiencies, this is a societal choice if we then choose to use our machines in the wrong way. But in the absolute, independently of societal and market choices, I declare here among physicists is good to increase efficiency. So I prefer going, posing the problem in that direction. So then only talking about efficiencies. So given this task, I have a classical computer and a quantum computer. Who will consume more? Actually, the difficulty of the question is that it really depends on in which way you picture yourself a quantum computer. There are some people who are more from the theoretical, say, quantum computing community, who will see the quantum computational advantage and will tell, there are less physical steps. So if there were less physical steps, then at the end of the day, there is less energy that is consumed. So this is the optimistic team. But then there is the guy who is actually building the quantum computer. And he sees the cryostat like this, with all the wires like this, with the error correction and the number of wires that increases exponentially. You say, this is not going to work. This is really going to cost a lot of energy. And you see, these two pictures, they are fully legitimate. So the problem here, that we cannot say yes or no, it will cost more or not, is simply that we don't have a methodology to address the problem correctly. So that's what we propose. We propose in the Quantum Energy Initiative to join forces and to create this new research line where basically we will be able to address the question in a less hand-waving way, which is currently the case in the community. So why is that so difficult to build this research line? It's because this is essentially interdisciplinary. And why is that so? So I'm coming back with this concept of efficiency. This is my quantum processor here. And I want this guy to have to realize a very good computation with a very high metric of performance. What is the condition for that? The condition for that is that the control here that I'm trying to have on my processor, it beats the noise. And this is all a fight that takes place at the quantum level. If control wins, then I have few errors and I have a good metric of performance. If noise wins, then I have a small metric of performance because I have many errors. But this is a fight that really takes place at the quantum place. And at this level, there are already a variety of approaches to mitigate noise, which is error correction, environment engineering, playing with the speeds, as we've seen with Ronnie. Qubit fabrication also plays a role. So you see there are already things to optimize at this level. And so I'm going a bit faster here because what I want to say, which is important, is that this beast here, the quantum processor that interacts with a little bit of remaining noise, but still quantum laws apply, it does not exist per se. It is not a physical situation that is given by nature. To reach this, we have to fight a lot because we naturally live in a classical world, and we need to fight to create and isolate pouches of quantum inside of this classical world. This is something that I would describe as the cost of classical control. And why has it a cost? It's because we have to create a quantum classical boundary. And this is essentially a non-equilibrium situation. And as soon as you play with situations that are non-equilibrium, you pay. You produce entropy and you pay a lot of work. So that's why I asked the question to Ronnie at the end of your talk. The big question, I would say, if you want to phrase it in very fundamental way of the QEI, would be to compute resource costs to trap a Schrödinger cat. And right now, what we did is just trying to control the decoherence of the cat. Yeah, but how do we create the cat in the first place? And what is the cost of the box around the cat? I would say that's the big problem, the cost of the classical context, basically. And right now, I've actually no idea of how to tackle this problem. I have the sad intuition that is a reformulation of the Heisenberg cut, but expressed in energetic terms. But yeah, I still find it cute. I hope we can, revisit this problem with energetic concepts. So now I conclude on this interdisciplinary challenge. This guy, as I was saying, does not exist. And then to reach this state here, this quantum states of my quantum processor, I need to involve macro control, which is basically the enabling technologies that we use to control the quantum computer, to isolate it and control it. So this is cryogeny, wiring, control electronics, lasers, detectors, everything that we use to control and measure. In other words, every bridges that we have between the quantum and the classical, they have a cost. So these are these macro resources. And then the real efficiency of quantum computing, it is the ratio between the performance that is reached here at the quantum level divided by the resource that is consumed here at the macroscopic level. So you see that the QEI, it's an attempt to connect the quantum and the classical for new purposes, in other words. So this actually, we created, we launched the Quantum Energy Initiative in August, last August. So these are my lovely co-founders. So Olivier Ezrati, who has always a dimensional energy. I don't know how it does, but the fact is that he's big momentum. Robert Whitney, who has been my co-worker for long years now, and Janine Spettosa, that some of you know very well. And so we have at this time launched a manifesto and a poll. And right now, actually, the QEI has become something that is less manifesto based. It's like for now, it's just a mailing list and the QEI community that you guys are welcome to join if you want to stay aware of what we will do, which will basically right now will be animation of the community and start to put people in contact, start exchanging knowledges and building roadmaps. These are the first partners of the QEI, because that was funny actually. When we launched this, you can talk to academics and you can talk to companies. And the companies were extremely reactive. They were much more reactive than the scholars, actually. I guess because they are much more, how could I phrase it? Maybe sometimes this is an image problem, but they are much more concerned for the image of the company of environmental problems. So they want to put that forward. Anyway, they were like very eager. Lots of them was very eager to sign up quickly. And since January, we have a nice board where you can recognize as well some faces. I mean, some face. I'm looking at it. So with a representation, something that we try to be broad in terms of countries or region of the world at least, and also skills, because as you saw, it connects fundamental quantum physics to cryogenists, to people who manage classical information processing and stuff. So we try to make it like broadband. And here are a few of the scientific questions that we want to address. So I showed you at the beginning the exploration of the energetic quantum advantage as quantum processors scale up, and how different the energetic quantum advantage would be different from the quantum computational advantage. Then this one that I like a lot, what is the minimal energy cost of quantum computing, but now taking into account this big classical context around. And one more technological problem is how can we avoid energetic dead ends on the road to large-scale quantum computing? And obviously, all the framework that we want to establish for computing, it's naturally transposable to the other quantum technologies like communication and metrology, because what I've shown you with the efficiency, you can apply it everywhere. It characterizes all machines, basically. It's running late, so I think what I want to, how tired are you? I'm tired, but and I don't want to, but I'm in a metastable state, so I can talk like blah, blah, blah. But I want you to be with you, otherwise I jump to the conclusions, and I'm also very happy with this. So you just let me know if you want me to talk like 5, 10, I can adapt. Just tell me and
Another 5 minutes.
5 minutes, perfect. How many slides? Yeah, so a bit of advertisement, because right now I advertise for the big initiative, which is worldwide, blah, blah, blah. And we also have some sort of proof of concept that we have applied in my group. Within a close collaboration between, a Singaporean colleague that now I've joined, but at the time I was in Grenoble, whose name is Wikun Eun, Robert Whitney, and the PhD student who was in charge was Marco Felusasiani, and he basically managed to play the quantum engineer here, and in his brain there was multidisciplinarity, because at the same time, he learned about fault tolerance with Wikun. And at the same time, he went to understand all of this, like the wires, the conduction, the different stage in the cryostat. And he did all of it together to build like a model of quantum computer that takes into account the full stack and all the resource cost. So I'm not going to enter more into the details, but he applied a very reasonable methodology to access this energy efficiency for quantum computing with a very idealized model of quantum computer. So for the specialist, I just say it. We pick basically Sycamore, so the processor of Google, but with very idealized superconducting qubits. So they don't suffer pure dephasing. So they have a 0 T2 and just a T1. And the T1 is already extremely good. And we apply error correction. You're using STEAM code, which is awful. in terms of resource consumption because it's exponential. At each level of concatenation, you pay a lot. But the advantage of the STEAM code is that it allows you to keep everything analytical. It's perfectly well documented. We know what we are talking about. And also the encoding, decoding is not problematic. It does not carry a lot of classical information processing, which we also expect to cost a lot. So here we just focused on the cryogenic and energy costs that come from the CMOS that is inside the quantum computer. And applying this, actually, we have played the game of computing the minimal power consumption for the quantum computer to break RSAK if it has like 829 bits. I managed to say it. And so with this, we already found a quantum advantage, because what you see is that the energy that is consumed in principle by this very idealized quantum computer is 100 less, well, almost 1,000 less than the one that is consumed by the classical supercomputer. And this was actually measured. And this is a result from INRIA. So they did the job, and that's also why we started exploring how it would go for a quantum one. And now if we go in the regime of true quantum supremacy, then obviously the energy that is consumed by a classical computer, it's way too much. Quantum computer is still there. Well, this is still like 40 gigawatt, but it's still doing the job for sure. So, and to break the 2048 bit K. So these results, obviously, they have to be taken with a pinch of salt, and lots of salt in your face, actually, because again, the qubits, they are really ideal. We entangle like zillions of them, but still it shows that we have a methodology. And if we apply it to an ideal computer, we can start exploring something which was not explored before, which is the energetic quantum advantage. And now the whole problem is to start doing this with more realistic models, something else than the thermal noise, and yes, start to do this with realistic parameters. And this is again the purpose of the QEI. Last thing I want to say is that what we got aware of doing this is that we realized, and I'm going to phrase it in a way that will appear to you as obvious, that searching for a quantum energy advantage is not the same as searching for a computational advantage. There are regimes that we singled out where actually you can find quantum processor that will take more time to do their job, but that will eventually consume less energy than the classical computer. And this we found as a side product, but actually we believe this is a very important message, especially for the NISQ community, where no quantum computational advantage was shown yet. But if we start putting figures, maybe we'll see that actually the NISQ device consume less, which makes a good reason to try to fabricate them either way. So yeah, and the bottom line is that optimizing time is not optimizing energy. It should be obvious, but actually if you talk to a decision maker and tell him, yeah, now you should fund the QEI because you know it's important energy, blah, blah, blah. Many guys will tell you, yeah, but you know, I'm already funding you to build the quantum computer. And if it computes faster, then it will consume less. So game over. And no, because the power is not the same, you know, energy is power times time. And but still, so it takes time to lobby people and to convince them that it's worth investigating the topic on its own. It's not the same thing that we are chasing. So these are the take-home messages. So quantum energy advantage, actually, I think it's a very nice prey. It's a huge potential practical interest of quantum computing that is, again, different from quantum computational advantage. And to explore it, we need to articulate these different levels of description in this new interdisciplinary research line. We have also a new benchmark, which is the quantum computing energy efficiency. And actually here I mentioned that I recently became chair of a working group at IEEE, where we are going to try to standardize, to make a standard, sorry, with this efficiency. And the idea is really to extend this after that to all quantum technologies. Last bit of advertisement before I stop talking. There will be the first in-person workshop for this quantum energy initiative that will take place in Singapore in next November. Yeah, Singapore was immediately funded this, like they are clearly interested also in working on the topics. There are very nice speakers that have already, so among which Christiane that you mentioned before, she will represent the quantum control part. And yeah, the deadline for submission, the first deadline for submission is late April. I mean, you are welcome to send contributions. Voilà, and I conclude on that.
Okay, thank you, Alexia. Do you have any questions from the audience?
Hey, Eric. You make an interesting point about how energy efficiency, quantum energy advantage is a different task than computational advantage. And it also strikes me that we're right now kind of short on useful things to use a large-scale quantum computer for, other than factor numbers. Do you think that there are, in this context, opportunities to look for different types of algorithms that would have this quantum energy advantage? Or is it like, is it a chance to really go back to the drawing board for quantum scientists and think of new algorithms with this new goal in mind?
So I don't know if it can impact the algorithm to search for, but it is certainly a new incentive. That's for sure. But I'm not sure it will renew the questions, actually, if we say the algorithm is the question. But it will renew the interest for this or that operating regime. That's for sure.
Other questions?
When you look at the sycamore, how much you can say energy is put into the dilution refrigerator and all the environment?
Actually,
What fraction of that?
say it again.
What fraction goes to the infrastructure, to the dilution refrigerator, controllers?
In the sycamore experiments, actually, they measured the cryogenic power. They had like 25 kilowatts. And that's actually one of the first papers where they have claimed to have also a quantum energy advantage, but without consolidating this. That was just somewhere hidden in the appendix. And so your question is, now that I know this cost, how can I know what goes in the environment and what goes to isolate the computer? Was that the question? Mm-hmm. So yeah, in the proof of concept that I shown, we computed actually, basically, we listed the different resources, and we know that for the architectures that we have considered, half of the energy was paid for the cryogeny. So basically to eliminate the heat that was dissipated inside the computer. And this heat is due to two major things. One is the conduction from the external room temperature inside the cryostat because of the wire that you use to control the processor. The other is when you drive your signal, you have these attenuators on the way to increase the signal over noise ratio. And basically, if you want to drive with X, you have to input like 10 to the power blah, X. And this is what is dissipated and that you have to evacuate after that. So this is half of the cost, and the other half comes from the CMOS, which is the electronics that you use both to shape your signals that you send to control your system, and also for the error correction. So both come on equal footing in the final bill. But you see, what I'm saying here is, yeah, it gives you an idea of why actually controlling noise with resources like error correction, it can eventually bring you to something that you don't want, which is bringing more noise in the game. You want to do error correction, you add qubits, but you need to control these qubits. And all these wires, they bring you more noise. So you have a closed loop here, and the goal of the initiative is precisely to address these saddle points that you can imagine will take place that mix like macroscopic parameters and quantum ones. So, and your models would fit very well, but then we would need to pick your noise and to take into account how is the environment, how are the macroscopic resources modifying the noise that you input in your optimizations. That would be closing the loop between quantum and classical.
So how are you getting, so you say you can have quantum energy advantage without the speed up, like what is the source of the energy advantage?
So that's a very good question, which would require we go a little bit deeper in the models. Let me see if I can come out with some like very basic idea of the origin of this. If you are not too tired, I can. There is a slide that, oh no, this is a slide that I had erased. I had a slide where I was showing. You're at the workshop tomorrow. I can answer you tomorrow. I'm afraid we're taking too much time here to answer.
Okay, let's thank Alexia again for the nice talk.